today. We're going to cover 6C today, which is properties of the normal distribution. This is the last section in chapter 6 that we're going to cover. And we'll also have a video on the mini project from chapter 6 before we move into probability. So I've made side by side right here so that you guys can see the notes that we have already available online. They're a little old, but they're still just as relevant as they were 2 years ago. So I'm going to use these kind of as some backdrop just to give you some rundown of what to expect in the normal distribution. And then we'll do some examples. The example that we have here on this page we'll do, and then I'll pull a couple examples up from MyMathLab as well. So what is the normal distribution? Uh, well, it's a distribution that appears most commonly in genetic, environmental, and manufacturing settings. We also know it as the bell curve. We have this real high peak in the middle, and we have these long tails to the sides. Distribution can take on, normal distribution in particular, can take on a couple different forms. The general shape of the distribution is the same, but depending on how spread out the data is, this curve can have a real tall peak in the middle, or it could have kind of a shorter wave that extends out in both directions. So there are a few properties of the normal curve that we have to keep in mind that allow us to draw that bell shape accurately. The mean, the median, and the mode are all equal. So in this middle area here is where most of the distribution is going to happen. So the mode, there are going to be more people in the middle than anywhere else. And also the fact that mean and median are equal gives us this balance right in the middle that we can build off of. The other thing about the normal curve that's really important is the idea of symmetry, that the data is symmetric about the mean. Later on, we're going to talk about the Six Sigma rule or the empirical rule, and it's going to cut the graph up into smaller pieces based on its standard deviation. But another thing to keep in mind in order to answer many of the questions is that the data is also cut directly in half around the mean. So if we were to split the curve right down the middle, 50% of it would be to the left of the curve, 50% of the data would be to the right of the curve. Also, there are outliers, just as there is in all distributions, and they're at the tails. We refer to those as usually more than 3 standard deviations away from the mean. So when we draw the normal distribution, we're going to be really interested in the mean and the standard deviation, which are really the only two characteristics that we need to draw the curve. And then the farther those distributions, the standard deviations are, then the farther that distribution is spread out. And then lastly, what we just discussed, that role of standard deviation. What it does is it breaks the normal curve up into parts. We have this one standard deviation plus or minus from the middle gives us 68% of the data. Two standard deviations from the center plus or minus gives us 95% of the data. And three standard deviations from the middle plus or minus gives us 99.7% of the data. So that is referred to as the Six Sigma rule here. And we have a nice curve here already drawn out. Again, we refer to the mean, whatever the mean is. We also note that as x bar. That is what we start our graph with. And then we take our standard deviation, whatever number that is, and we apply it to the mean. So as we go to the right, we're adding standard deviation each time we go. And we want to go 3 out to the right, and then we subtract standard deviation as we go to the left, 3 to the left as well. So we have a total of 7 values here on the bottom. The middle, and then 3 to the left, and 3 to the right. So we're going to do this example down here. And it says SAT scores are distributed with a mean that's equal to 1,000. And we have a standard deviation that's equal to 200. So this is what we know about the distribution in the beginning. And again, these are the only two things that we need to know about the distribution in order to draw it. The first thing it says is we want to create the distribution for the following setting. So it's not something that you're asked to do in MyMathLab only because they're just multiple choice questions, but it's something that you should definitely be familiar with. If I give you the mean and the standard deviation, be sure that you're comfortable in drawing the normal curve. So we're going to go over here, we're going to draw ourselves a little distribution. Mine isn't great, so just bear with me. I can do better than that. There. It said that the mean was 1,000. So on average, a student scores 1,000 on the SAT, and the standard deviation is 200. So what we want to do is we're going to go add 200 to this value each time we go to the right. So we have 1,000 there, then we're going to have 1,200. We add 200 more, we got 1,400, and then lastly, way out at the end of our distribution, we have 1,600. And same thing going to the left, except now we're subtracting. So over here to the left, we're going to have something like 800. And then if we subtract 200 more, then the second standard deviation to the left is 600. And then lastly, all the way over here, we would have a 400. And again, application of the Six Sigma rule tells me that 68% of the data is going to be in between 800 and 1200. So 68% of students are going to score between 800 and 1200 on this exam. Then I go out one more standard deviation. Between 600 and 1400, we have 95% of the data. And then lastly, from 400 all the way up to 1600 is 99.7% of all data. So this question first asks us, what percent of students score between 600 and 1400? So we look at our distribution here, and we start by finding these values that they're interested in. 600 we can see lands on the 95% value in this range here, and 1400 is the endpoint. So actually, we didn't have to do much arithmetic in this at all. It turns out that the range between 600 and 1400 makes up 95% of the data. So we can say 95% score between 600 and 1400. The second one says, what percent of students score between 1,000 and 1,200? Well, 1,000 is right in the middle. And remember, we mentioned before that data is symmetric about the mean. So if I use this line right here, what it does is it tells me that 50% of the data is going to be here going to the left, and then I have 50% of all data here moving to the right. This question asks us specifically about scores between 1,000 and 1,200. Well, if I look at 1,200, which is the score that we're interested in this problem, the 1,200 falls along the 68% bracket, if you will. So because it ends up right here at the end of this 68%, I know that I want to use 68% in some way in my calculation. Now, if the question asked between 800 and 1200, my answer would be exactly 68. But it asked between 1000 and 1200, and remember that 1000 is that halfway barrier in between these two values. So in between 800 and 1200 is 68%, and if I cut that value in half, what it tells me is 34% is going to be between 1000 and 1200, and another 34% would be in between 800 and 1000. So we can always use that middle point kind of as a way to cut values in half. Again, this question was asking us in between 1,000 and 1,200, and so the value that we're looking for is 34%. So we can make the statement 34% of students score between 1,000 and 1,200. And then lastly, the question said, what percent of students score between 600 and 800? And here is where we're going to have to start getting a little bit trickier with what we do. So between 600 and 800 uses two different values in the Six Sigma rule. Remember that the 800 falls along the 68th percentile, and that the 600 falls at the end of the 95 percentile, or the 95% group in the middle, I should say. So what we're interested in is actually this shaded area right here. For the more complicated problems, I like to shade in the area of the graph that I'm looking for, because then it allows me to use some math to solve it. When I have a visual picture of it, it's much easier for me to construct the problem. So remember that if I were to go from 600 all the way to 1400, that would be 95% of the data. And if I were to go from 800 to 1200, that would be 68% of the data. Because I'm only looking at this area between 800 and 600, I would want to subtract the larger percentage minus the smaller percentage. But that's only going to give me what's happening in the left half of this problem. And so this shaded area can be expressed as 95% minus 68%. But again, we're only using this half of the square, or this half of the distribution here. So I need to take this whole answer and divide it by 2. This gives me 27% divided by 2, or 13.5%. So that little sliver right there is about 13.5% of all the data. In the notes, there's a nice little picture that's broken some of those distributions up for you already. Although it is missing 2 pieces, so I'm going to redraw it right here for more reference. So remember we said that this area right here was 68% if I go from the mean to 1 standard deviation in each direction. I'm going to take that and I'm going to split it up. Sorry, my picture is really not very symmetric. I'm going to take that value and I'm going to split it up, remember cutting it in half. So I'm going to say that 34% lies here and 34% lies here. If I go out 2 standard deviations, remember that was 95% of the data. But if I subtract 95% minus the 68 in the middle, I get 27%, like we did in the last problem. And cutting that value in half tells me that the area between 1 standard deviation and 2 standard deviations on each side is 13.5%. 13.5%. The area between 95% and 99.7% can be found by taking 99.7 minus 95 and dividing that value by 2. That gives me each of these tails between 2 standard deviations and 3 standard deviations is 2.35%. 2.35%. You may notice on the notes that it says 2.5% right here, but that's actually from 2 standard deviations all the way out forever. And what it's not keeping in mind, or what it's not considering, is this tiny little tail over here beyond 3 standard deviations. Remember that when you're beyond 3 standard deviations, you are in the 0.3% of all the people that are left. And so this last little tail right here and this last little tail right here can be found by taking 100 minus 99.7 and dividing that by 2. So these tiny little slivers, the outliers, if you will, end up being 0.15% on each side. So this is another geometric way of looking at all the different values in here. Some people really prefer to look at the curve in this way, and now they can just identify what parts they have to add together. So if you prefer to do it this way, it's certainly fine. On the exam, the only notes though that you will be given is a curve that shows you 68, 95, and 99.7. So one more concept in 6C to talk about, and that is the concept of z-score. Z-score is a measure. It could be positive or negative that defines the number of standard deviations you are away from the mean. So in the previous example, we had a curve that had 1,000 in the middle, and then I'm just going to go one standard deviation out. Remember, the standard deviation was 200, so when we went to the right, it was 1,200, 1,400, and so on and so forth. Actually, I guess I can write them out. 1,400, 1,600. Going to the left, remember, it was 800, 600, and 400. The z-scores associated with these values. In the middle, if you're right at the middle, then your z is 0. You're no standard deviations away from the middle. You're right at the middle. As you go to the right, you're adding 1 to these. So 1,200 would be the same as z equals 1. 1,400 would be the same as z equals 2 because I'm 2 standard deviations away from the mean, and so on. Going to the left, it's the same idea, but now your z values are negative. This would be -1. I've subtracted 1 standard deviation from the mean. Here I've subtracted 2 standard deviations from the mean. At 400, I've subtracted 3 standard deviations from the mean. So this is how we would label those in terms of z-score, looking at the previous example. In general, z-score can be calculated by doing this. We take the observation, whatever one they give us, and from it we subtract the mean. Once we get that value, we divide the whole thing by the standard deviation. So we'll pull up an example real quick, just so that we're all comfortable with defining z-score. I'll just grab one from MyMathLab. So this problem says, scores on a psychology exam were normally distributed with a mean of 63 and a standard deviation of 8. What is the standard score for an exam score of 59? And here it told us that we want to round to the nearest hundredth as needed. So we'll write down the important information here. We said that the mean, or x bar, is 63, and that the standard deviation is 8. They want to know what is the z-score, and they gave us an observation that was 59. So if we want to calculate the z-score, remember, we take the observation minus mean, observation minus mean, all over standard deviation. So we get z is equal to 59 minus 63. Notice that our observation is smaller than the mean. In the distribution, we would be on the left of the bell curve. And the z-score is going to be negative as a result. Standard deviation was 8. So here, 59 minus 63 is -4 over 8, which is negative 0.5. Z-score is usually written in a decimal. MyMathLab likes you to round to the second decimal place to the nearest hundredth. That's perfectly fine. Depending on how accurate you need to get, some z-scores will go farther back than that, maybe 3 decimal places, but you're fine to keep it at 2. At this time, I also wanted to talk to you briefly about what's covered in the mini project 6. So mini project 6 is online now. The key will be posted on Wednesday. The homework's not due till Friday, though. It's due with the rest of Chapter 7, which will begin tomorrow. In the mini project 6, the beginning asks us to find the measures of central tendency for a data set. The data set I grabbed from online, just the median household income from 20 states in the US. And so in here you can calculate the mean, the median, and the mode for the data set. Remember, mean, we add them all up and we divide by the number of observations. The median is the middle observation. And I don't know if, oh yeah, I guess you can see that now. What you can tell here is actually for the median, you'll be looking at the middle observation, and they're arranged from smallest to largest going from left to right. So the middle observation is actually going to be in between 63,938 and 65,012. Remember, to find the median, we take the average of those two. So you should be taking the average of these two values here that I shaded up in the top right. And the mode is just the one that appears the most. Hopefully there's one of these that has a repeat. It also asks you to calculate the standard deviation for the 4 largest values of the data set. So you don't need to go through the process of calculating the standard deviation for the whole thing. That's just like super rude. It'd take you a while. But you can use Excel for this too. So if you are a tech savvy person, you can use Microsoft Excel as a really good helpful tool here. Let me just pull up a new sheet here. And so you can take these numbers and you can plug them in. For example, if you wanted to do the 4 largest values of the data set, they are 80,108, 85,750, 86,223, and 86,349. Again, you can do this for part 1 as well if you want to find the mean, median, and mode without having to do it manually. You should be familiar with doing it manually, but really, in real life, calculations have data sets that are huge, and you wouldn't be doing it by hand. A software program would be much more helpful. So I'll show you really quick. If you wanted to calculate, for example, the average of these, then in a cell somewhere nearby, I like to use the cell below it, I'm going to put in equals, and then I'll type in average. And then it asks me to tell it what cells I want it to take the average of. So I like to just click and drag. I'm going to click on the top one and drag down until I get the bottom one. Then I'll press equals here. And this is the average of those 4 values. If I wanted to calculate the standard deviation, I can do the very same thing. I'm going to put in equals, and then I'm going to start writing in stdev is the one we want. Notice that there's more than one standard deviation. We discussed this before in 6b when we talked about standard deviation. The one you'd want to use is standard deviation with the S on it. We're taking the standard deviation of a sample. The standard deviation with the P is standard deviation of a population, which we don't know the whole population. So we take the sample standard deviation, and again it asks me for which cells do I want to put in here. So I'm just going to click and drag these 4 cells right here and press equals, and that value right there is the standard deviation for the data set. Notice that the data set has 5 significant figures in the beginning. It would be useful to have 5 significant figures here. That would be one way of doing it. These are also money calculations, so you could have also justified these answers by rounding to the nearest cent. That would be cool too. I would take either one of those, frankly. But in terms of precision, I would go with one of those two. Either go with 5 significant figures or round to the nearest cent. Going back to the mini project, they also want us to find the 5-number summary. 5-number summary can also be found in Excel. You can look for a function called quartiles, and it'll give you what this quartile 1 and quartile 3 are. I believe you could probably do that as well, though, just by looking at the data, right? You can find the median. It's going to be the average of these two. And then quartile 1 would be the middle of this first row. Quartile 3 would be the middle value of the second row. Min and max, pretty straightforward. Interquartile range don't know if we talked too much about this, but IQR is Q3 minus Q1. So once you find the first quartile and the third quartile, you can subtract these values in order to find your interquartile range. On the back side, it asks you to sketch a box and whisker plot of this distribution, which you should be familiar with, and then tell me if you found any outliers or if you think that there are any that exist. Part 2 is the application of what we just did in lecture, which is all of the empirical rule or Six Sigma rules. Here it tells us that the babies are normally distributed with a mean of 3,000 grams and a standard deviation of 700. So sketching the distribution should be pretty familiar at this point. You should have 3,000 in the middle, and then as you go to the right, adding 700, 3,700, 4,400, 5,100. And as you go to the left, subtracting 700, 2,300, 1,600, 900. Then we want to use the empirical rule to answer the questions in number 8. Find the proportion of babies that have weights between 1,600 and 4,400. Notice that 16 and 44 are both 2 standard deviations away from the middle. 2 standard deviations away from the middle makes up 95% of all the data. I'll do one more. Find the proportion of babies that have birth weights between 2,300 and 5,100 grams. Remember that 2,300 to 3,000 makes up 34% of the data. Remember that 23 lies on the 68% rule, but if I wanted to just go from 23 to 3,000, that would just be half of the 68 rule. So I'm going to write that out as 34%. And then to go to 51, remember 51 is way out here at 99.7 of the data that goes from 900 to 51. But really, in order to answer this question, I just need to know from 3,000 to 5,100. And so that's going to be half of 99.7. So to this 34, I'm going to add 99.7% divided by 2. Together that gives me 83.85%. I'll leave it to you to answer C and D. And like I said, the key for this will be up here probably in the next day or so. And we probably won't even wait till Wednesday. If you have any other questions, of course, you know where to find me. Hope you have a great day. This concludes Chapter 6 now. And next time you see my face, we'll be talking about probability. Have a great day.